For decades, biology operated on the assumption that aging was a one-way accumulation of damage. Recent laboratory experiments have effectively dismantled that model. By transiently expressing specific transcription factors, known as Yamanaka factors, or OSK or OSKM, researchers have successfully lowered the epigenetic age of adult tissues in vivo. These studies reveal a striking result. The age reversal happens while the adult cell maintains its somatic identity. Short bursts of these reprogramming factors reduce molecular markers of age and improve regenerative capacity. Yet a liver cell remains a liver cell, and a retinal cell remains a retinal cell. A system defined by mechanical wear and tear cannot selectively reverse its damage while keeping its highly specialized architecture intact. The ability of a cell to rewind its molecular clock without erasing its mature form suggests that age is distinct from the accumulation of irreversible temporal decay. In this light, biological age behaves as a plastic, measurable, and partially reversible state variable. Treating age as a state variable requires a radical shift in theoretical biology, necessitating an ontology where elapsed duration is no longer the absolute driver of biological decline. The TCGS-SEQUENTION framework addresses this shift by defining time as a foliation label. In this model, time serves as a useful ordering system for tracking change, but it lacks the ontic power to physically act upon a biological system. Observable biology exists within what TCGS calls the shadow manifold, a multidimensional landscape of regulatory and genetic constraints. Within this manifold, a youthful biological state corresponds to a deep, highly stable organizational basin. A system residing in this attractor basin operates with high coherence and functional resilience. Aging manifests as canalization drift. Under the weight of unresolved constraints and senescence, the biological system physically drifts away from the youthful attractor basin and into the flatter, unstable regions of the manifold. This geometric displacement redefines rejuvenation as a spatial navigation problem, where the goal is to steer the system back into its stable, youthful valley. Modern biogerontology tracks this navigation using multi-omic tools, specifically DNA methylation and transcriptomic clocks, to provide an estimate of biological age. These clocks function as shadow coordinates. They are partial, two-dimensional projections of a complex 3D biological landscape. When a cell moves within this 3D landscape, its position projects onto these planes. The age readouts shift because the underlying biological organization has relocated. This geometry explains structured clock discordance, where an intervention might lower a methylation clock but leave the transcriptomic clock unchanged. The cell is moving at an angle that appears significant on one flat projection while remaining stationary on another. Because individual clocks are only projections, true rejuvenation requires moving the entire system back into its stable attractor basin rather than manipulating a single coordinate. Safely navigating the shadow manifold requires a formal restoration geometry to avoid the various biological hazards that surround the youthful basin. This grid defines three axes: age on Z, lineage identity on X, and malignancy on Y. Successful rejuvenation stays within this safe corridor. However, continuous reprogramming often causes corridor overshoot. The trajectory violently exits the corridor into dysplasia or teratoma formation. The safety of longevity interventions depends on the ability to solve this strict topological boundary problem. This geometric model identifies the clear distinction between reversing age and reversing cancer. While the two fields overlap, they begin from very different positions in the manifold. An aged cell sits high on the age axis, but inside the safe corridor. A cancer cell is epigenetically young but far outside the corridor due to malignancy. Reversion strategies and rejuvenation protocols both steer these distinct cells toward the same adult tissue-compatible basin. Cancer reversion recovers tissue compatibility without necessarily lowering the biological age of the cell. Similarly, rejuvenation lowers the age coordinate but carries the risk of triggering oncogenic instability. Because these coordinates are independent, an improvement in one must be validated against the others to ensure the cell remains within the safe corridor. Chemical cocktails, senolytics, and epigenetic editing serve as localized control handles. They act by altering the accessibility gradients of the manifold, making the youthful basin easier to reach. A cell's internal state is conditioned by its surrounding neighborhood. Changes in local tissue architecture ripple through the network, physically reshaping the entire biological manifold. Spatial aging clocks show that local niche geometry dictates age. A pro-inflammatory T-cell neighborhood flattens the youthful basin of nearby cells, while a neural stem cell niche deepens it, providing pro-rejuvenating support. Rejuvenation requires more than cell-autonomous changes. It demands the architectural remodeling of the local spatial ecosystem. The TCGS-SEQUENTION framework provides a cartographic map for future longevity research, offering 10 falsifiable predictions that define a clear scientific program. The prediction of convergent endpoints suggests that radically different interventions will produce identical multi-omic signatures if they successfully access the same youthful attractor. Because shadow age and malignancy are independent coordinates, researchers must match interventions for clock-lowering effects, then test if they carry different oncogenic risks. The ultimate proof of a stable basin transfer is post-withdrawal retention. A true rejuvenation event must persist after the initiating intervention is removed, distinguishing it from temporary state forcing. Success in the longevity field will be measured by the achievement of multi-map coherence, rather than the speed at which a single biomarker can be changed. Longevity is defined by the sustained residence of a biological system within a coherent, functional basin. Biogerontology serves as a method for the geometric recovery of these stable organizational attractors. True rejuvenation involves successfully navigating the biological shadow, preserving lineage identity, and mastering the boundaries of the safe corridor.